Let's understand what prompt compression is. Prompt compression is the process of reducing the number of tokens in a prompt while preserving its meaning and intent. For example, a 500-token prompt can often be compressed to around smaller tokens like 200, 300, etc., while still giving the language model almost the same instructions. But before we understand prompt compression in detail, let's first understand what a token is. Language models don't read a sentence as one piece of text. They first break it into smaller units called tokens. Each token is first assigned a unique token ID. The language model then uses that ID to look up an embedding, a vector of numbers that captures the token's meaning. These embeddings are what the model actually processes. Now that we know what prompt compression is, the next question is, why do we even need it? The biggest reason is cost. Whenever we use a large language model, we're usually charged for two things: the input tokens we send, which is part of a prompt, and the output tokens the model generates. Imagine prompt contains 500 tokens. After prompt compression, it becomes just 200 tokens. That's a reduction of 300 input tokens, about 60% fewer tokens to pay for. Across thousands or even millions of API calls, the savings quickly add up. A shorter prompt also means the model has less information to process, which often leads to lower latency and faster responses. Prompt compression removes redundant information and keeps only what's important. With less unnecessary context competing for attention, the model is more likely to stay focused and produce better quality answers. Prompt compression is especially useful in RAG. Along with the user's question and conversation history, retrieved documents can quickly consume the available context window. Compressing those documents preserves the key information while freeing up space for the model to generate a better response. So, prompt compression offers four major benefits. It reduces input token costs, improves response speed, helps the model focus on the most relevant information, and makes much better use of the context window, especially in RAG applications. Now, let's explore two popular prompt compression techniques used in RAG. The first is embedding-based filtering, which removes irrelevant chunks. The second is LLM-based compression, where a smaller language model or cheaper model extracts only the information needed before passing it to the larger model. Before applying prompt techniques, let's first build the RAG knowledge base. We upload the documents, convert them into embeddings, and store those embeddings in a vector database. This allows us to efficiently retrieve relevant information for every user query. For demonstration purposes, we'll use LangChain's Wikipedia loader to fetch a few Wikipedia articles. These articles act as our raw documents and form the knowledge base for our RAG pipeline. If you're new to LangChain, it's an open-source framework that offers a collection of reusable components for building LLM-powered applications. Next, we split each document into smaller chunks so that retrieval becomes more precise. Each chunk is then converted into a high-dimensional embedding using OpenAI's embedding model. These embeddings capture semantic meaning, allowing us to retrieve information based on similarity instead of exact keywords. Finally, we store all the embedding vectors in a face vector database. Face is an open-source library developed by Meta that enables fast and efficient similarity search over high-dimensional vectors. Now we will see our RAG pipeline by putting everything together. When a user submits a query, we first convert it into an embedding and use it to search the vector database. The retriever then returns the top K most relevant document chunks. This is where prompt compression comes into play. We either filter out less relevant chunks using embedding similarity or compress each chunk using a smaller language model. The resulting compressed context is then passed to the larger language model, which generates the final answer. In this example, based on user query, we're retrieving the top 10 matches. However, not every retrieved chunk is equally relevant. Our first prompt compression technique is embedding-based filtering. After retrieving the top document chunks, we compare the embedding of each chunk with the user's query and compute a similarity score. We then define a similarity threshold, in this example, 0.6. Any chunk scoring below this threshold is discarded, while the remaining chunks are passed to the language model. Notice that we're not modifying the content of the chunks here. We're simply removing those that aren't relevant enough. Our second prompt compression technique is LLM-based compression. Instead of removing entire document chunks, we use a smaller language model, GPT 3.5 in this demo, to compress the retrieved content. Its job isn't to answer the user's question. Instead, it reads each retrieved chunk and extracts only the information that's relevant to the query, removing unnecessary details. These compressed chunks are then passed to the larger language model, such as GPT-5, to generate the final answer. This significantly reduces input token cost while preserving the important context. We can also leverage other small language models, like the ones shown here. They offer an excellent balance between cost and performance. In practice, these two techniques are often used together. Embedding-based filtering first removes less relevant chunks, and LLM-based compression then extracts only the most useful information. This results in lower costs, faster responses, better use of the context window, and ultimately, higher quality answers.